For line to neutral loads, the neutral conductor can indeed be sized based on the calculated currents. This is provided for in the National Electrical Code, specifically in section 310.15b4. This section outlines the rules for sizing neutral conductors. Where the calculated neutral current exceeds 200 amps, the neutral conductor shall be sized not less than the calculated neutral current, unless otherwise permitted in 310.15b4-f. Section 310.15b4 addresses situations with unbalanced line to neutral loads. This section states that for line to neutral loads having a maximum imbalance of more than 20% of the line to neutral load current, the neutral shall be computed using the maximum imbalance and multiplied by 1.25. Therefore, the National Electrical Code provides guidelines for sizing neutral conductors based on the calculated neutral current. However, with unbalanced loads, it may be necessary to upsize the neutral conductor. In the specific case of a 480W/277 volt system, serving line to neutral loads, if there's a minor imbalance resulting in comparatively small currents in the neutral conductor, you can size the neutral based on these calculated currents subject to the stipulations within the National Electrical Code. The first key consideration is the magnitude of the neutral current itself. If the calculated neutral current exceeds 200 amps, the code mandates that the neutral conductor be sized no smaller than this calculated value. This requirement ensures that the neutral conductor has sufficient capacity to safely carry the anticipated current. The second critical factor is the degree of unbalance in the line to neutral loads. National Electrical Code section 310.15b4 specifically addresses this scenario. If the maximum imbalance exceeds 20% of the line to neutral load current, a further adjustment is required. In such cases, the neutral current must be calculated based on the maximum imbalance, and then this calculated value must be multiplied by a factor of 1.25. This upsizing ensures that the neutral conductor can adequately handle the potential increase in current due to the imbalance. In summary, for a 480W/277 volt system with line to neutral loads and a minor imbalance, the neutral conductor can be sized based on the calculated currents, but only if the imbalance remains at or below 20%. If the imbalance surpasses this threshold, the neutral conductor must be sized by multiplying the calculated neutral current based on the maximum imbalance by 1.25. This ensures compliance with the National Electrical Code and maintains the safety and reliability of the electrical system. Always consult the latest edition of the National Electrical Code and consult with a qualified electrical engineer or inspector for specific applications to ensure compliance and safety. Understanding the nuances of neutral conductor sizing is crucial for ensuring the safe and efficient operation of electrical systems, particularly in commercial and industrial settings where 480W/277 volt systems are commonly employed. The National Electrical Code provides the essential guidelines for determining the appropriate size of neutral conductors, taking into account factors such as the magnitude of the neutral current, the degree of load imbalance, and the specific characteristics of the electrical system. Incorrectly sized neutral conductors can lead to a range of problems, including overheating, voltage drops, and even electrical fires. Therefore, it's imperative to carefully consider all relevant factors and adhere to the requirements outlined in the National Electrical Code. Sizing the neutral conductor correctly is essential for ensuring the safety and reliable operation of any electrical system. It's a fundamental aspect of electrical design and installation that should never be overlooked. National Electrical Code section 310.15b4 provides the framework for determining the appropriate size of neutral conductors, and it's crucial to understand and apply these guidelines correctly. Let's delve deeper into the key considerations for neutral conductor sizing, particularly in the context of 480W/277 volt systems with line to neutral loads. Firstly, it's important to accurately calculate the neutral current. In a balanced three-phase system with purely linear loads, the neutral current would theoretically be zero. However, in real-world scenarios, perfectly balanced conditions are rarely achieved. Load imbalances, harmonic currents, and other factors can all contribute to current flow in the neutral conductor. The National Electrical Code recognizes this reality and provides guidance for sizing the neutral conductor based on the actual calculated neutral current. If the calculated neutral current exceeds 200 amps, the neutral conductor must be sized no smaller than this value. This requirement is in place to ensure that the neutral conductor has sufficient ampacity to safely carry the anticipated current without overheating or experiencing excessive voltage drops. Secondly, it's essential to assess the degree of load imbalance. National Electrical Code Section 310.15b4 specifically addresses situations where the line to neutral loads are significantly unbalanced. If the maximum unbalance exceeds 20% of the line to neutral load current, the neutral conductor must be further upsized. In these cases, the neutral current must be calculated based on the maximum unbalance, and then this calculated value must be multiplied by a factor of 1.25. This additional upsizing is necessary to account for the increased current that can flow in the neutral conductor due to the unbalance. The 1.25 multiplier provides a safety margin to ensure that the neutral conductor can handle the increased current without exceeding its ampacity rating. To illustrate this concept, consider a scenario where a 480W/277 volt system is serving a mix of lighting and receptacle loads. Suppose that the calculated neutral current under balanced conditions is 150 amps. However, due to variations in occupancy and equipment usage, the actual load on each phase varies, resulting in an unbalanced condition. If the maximum imbalance exceeds 20% of the line to neutral load current, the neutral conductor must be sized based on the maximum imbalance. Let's assume that the maximum imbalance results in a calculated neutral current of 250 amps. In this case, the neutral conductor must be sized to carry at least 250 amps multiplied by 1.25, which equals 312.5 amps. This means that the neutral conductor must have an ampacity rating of at least 312.5 amps to comply with the National Electrical Code. It's important to note that the National Electrical Code provides various exceptions and allowances that may permit the use of smaller neutral conductors in certain situations. For example, National Electrical Code Section 220.61 allows for a demand factor to be applied to the neutral load calculation in some cases, which can reduce the required size of the neutral conductor. However, it's crucial to carefully review the applicable code sections and consult with a qualified electrical engineer or inspector to ensure that any exceptions or allowances are applied correctly. In addition to the National Electrical Code requirements, it's also important to consider other factors that may influence the appropriate size of the neutral conductor. These factors include the ambient temperature, the type of insulation used on the conductor, and the presence of harmonic currents. High ambient temperatures can reduce the ampacity of conductors, so it may be necessary to upsize the neutral conductor to compensate for this effect. Similarly, the type of insulation used on the conductor can affect its ampacity rating, so it's important to select a conductor with an appropriate insulation type for the application. Harmonic currents can also increase the current flowing in the neutral conductor, so it may be necessary to upsize the neutral conductor to accommodate these currents. To summarize, sizing the neutral conductor correctly is a critical aspect of electrical design and installation. The National Electrical Code provides the essential guidelines for determining the appropriate size of neutral conductors, taking into account factors such as the magnitude of the neutral current, the degree of load imbalance, and the specific characteristics of the electrical system. By carefully considering all relevant factors and adhering to the requirements outlined in the National Electrical Code, you can ensure the safety and reliable operation of electrical systems. It is very important to consult the latest edition of the National Electrical Code and seek guidance from a qualified professional. Let's further break down the key aspects of National Electrical Code Section 310.15b4 and 310.15b4 concerning neutral conductor sizing, particularly focusing on their practical application in 480W/277 volt systems with line to neutral loads. This will provide a more comprehensive understanding of how to apply these code requirements effectively. Firstly, let's re-emphasize the importance of accurately calculating the neutral current. As mentioned earlier, the neutral current is not always zero, even in what might appear to be a balanced system. Factors such as single-phase loads, nonlinear loads producing harmonic currents, and variations in phase voltages can all contribute to neutral current. To accurately calculate the neutral current, it's essential to consider all of these factors. This may involve using specialized equipment, such as a power quality analyzer, to measure the actual currents flowing in each phase and in the neutral conductor. Once the neutral current has been accurately determined, it's important to compare this value to the 200 amp threshold specified in National Electrical Code Section 310.15b4. If the calculated neutral current exceeds 200 amps, the neutral conductor must be sized no smaller than this value, regardless of the degree of load imbalance. This requirement is in place to ensure that the neutral conductor has sufficient ampacity to safely carry the anticipated current. Secondly, let's delve deeper into the concept of load imbalance and its impact on neutral conductor sizing. Load imbalance refers to the condition where the currents flowing in each phase of a three-phase system are not equal. This can occur for a variety of reasons, such as uneven distribution of single-phase loads, variations in equipment usage, or faults in the electrical system. The degree of load imbalance is typically expressed as a percentage of the average phase current. For example, if the average phase current is 100 amps and the maximum difference between any two phase currents is 20 amps, the load imbalance would be 20%. National Electrical Code Section 310.15b4 specifically addresses situations where the load imbalance exceeds 20%. In these cases, the neutral conductor must be further upsized to account for the increased current that can flow in the neutral conductor due to the unbalance. The code requires that the neutral current be calculated based on the maximum unbalance, and then this calculated value be multiplied by a factor of 1.25. This additional upsizing provides a safety margin to ensure that the neutral conductor can handle the increased current without exceeding its ampacity rating. To illustrate this concept further, let's consider a practical example. Suppose that a 480W/277 volt system is serving a mix of lighting, receptacle, and motor loads. The calculated neutral current under balanced conditions is 180 amps. However, due to variations in equipment usage, the actual load on each phase varies, resulting in an imbalanced condition. The measured phase currents are 120 amps, 150 amps, and 200 amps. The average phase current is 120 plus 150 plus 200/3 equals 156.67 amps. The maximum difference between any two phase currents is 200 minus 120 equals 80 amps. The load imbalance is 80/156.67 asterisk 100% equals 51.6%. Since the load imbalance exceeds 20%, the neutral conductor must be sized based on the maximum imbalance. The neutral current is calculated as 200 amps, the maximum phase current multiplied by 1.25, which equals 250 amps. Therefore, the neutral conductor must be sized to carry at least 250 amps to comply with the National Electrical Code. In addition to these core requirements, it's also important to be aware of the various exceptions and allowances that may permit the use of smaller neutral conductors in certain situations. For example, National Electrical Code Section 220.61 allows for a demand factor to be applied to the neutral load calculation in some cases, which can reduce the required size of the neutral conductor. However, it's crucial to carefully review the applicable code sections and consult with a qualified electrical engineer or inspector to ensure that any exceptions or allowances are applied correctly. Furthermore, it's important to consider the impact of harmonic currents on neutral conductor sizing. Harmonic currents are non-sinusoidal currents that can be produced by nonlinear loads, such as electronic ballasts, variable frequency drives, and computers. These harmonic currents can significantly increase the current flowing in the neutral conductor, even in what might appear to be a balanced system. To account for the impact of harmonic currents, it may be necessary to upsize the neutral conductor beyond the requirements specified in National Electrical Code Section 310.15b4 and 310.15b4. The specific amount of upsizing will depend on the magnitude and characteristics of the harmonic currents present in the system. In some cases, it may be necessary to use a dedicated neutral conductor that is specifically designed to handle harmonic currents. In conclusion, sizing the neutral conductor correctly in a 480Y/277 volt system with line to neutral loads requires a thorough understanding of the National Electrical Code requirements as well as the specific characteristics of the electrical system. It's essential to accurately calculate the neutral current, assess the degree of load imbalance, and consider the impact of harmonic currents. By carefully considering all of these factors and consulting with a qualified electrical engineer or inspector, you can ensure that the neutral conductor is sized appropriately for the application, providing for the safety and reliability of the electrical system.